Welcome back for the last 45 minutes, or actually slightly less than 45 minutes of this spring session of the course. And I hear great rejoicing already from all the people at home. I hear there are parties going on. I mean, loud music, you cannot hear it. Neither can I, but it will happen as soon as the lecture is over, I'm sure. Or probably people will wait until after the exam for that. We will see. Anyway, so we still have some time to flex our mental muscles and practice. So what we're going to do now is to look at some topics related to vectors and vector geometry. Not because anybody specifically, well, actually, Baldur asked for that last time around. So I'm not making this up. In particular, he actually, if I remember correctly, he was asking that we would look at a type of exercise that you've been solving a few times and that somehow collects different topics that go under the heading of vector geometry. So suppose somebody asks you, okay, so I have a line that goes through a given point, P0, and let's say that this point has coordinates 1, 2, 3, that's good enough for me. And then we use this line as a direction vector, which is, well, let's make it 1, 0, 1. Why not? Just to keep things as simple as possible. Now let's pick another point. Let's call it P. That's always a lovely name for a point. And let's say that its coordinates are 0, 1, 4. Nothing specifically holy about these numbers. They're just small. And now somebody, for instance, me or the exam paper, asks you to find the shortest distance from P to the line. And the line goes through this point here and there's this direction vector. So how do you go about solving such an exercise? Well, for this type of exercise, there is an algorithm, which in fact has been spelled out also on Piazza in one of the shower of instructor notes that you may have received over the last few days or so, or throughout the semester for what matters. So without being overly true to life, so let's, so that's the direction vector here. And let's assume that our P is somewhere here. It doesn't have to be there. So this point P is here on the line. On the line, I said, Luca. And this is my point P. Okay? So I want to actually compute the distance between P and this line. So I want to compute the distance, which is the length of this vector, which I'm now writing in blue. So how do you solve this type of exercise? You want to start, as your colleague is saying, by finding the vector between P0 and P. Actually, what you want to do at the end of the day is to use a friend that you have met many years ago in earlier school grades, namely Pythagoras' theorem. Okay, so the vector here that goes from P0 to P, that's really the hypotenuse of a right triangle. Okay, in 3 dimensions in this case, but that's what it is. Okay, so how do I compute the vector that goes from P0 to P? It's P minus P0. So it's 0, 1, 4. That's the tip of the vector minus the tail coordinates, which is 1, 2, 3. Okay, that's a component-wise subtraction. So the result is 0 minus 1, that's minus 1. 1 minus 2, that's minus 1. 4 minus 3, that's 1. Okay, so now I know what the vector from P0 to P is. Now, if you want, all I need to do is to compute the green vector here that I get here. Why? Because once I know the green vector, I can compute the blue vector. Because the green vector plus the blue vector is nothing but the red vector that goes from P0 to P. Because if I start here, I follow the green, I get here. Then I follow the blue vector, I get here, which is P actually. So what the distance that I've traveled is the distance from P0 to P. And I've gone in the direction of the vector from P0 to P. So if I actually know, and I already know actually what the red vector is, let's call it U for consistency. If I find out what the green vector is, let's call it U1, then I know what the blue vector is. Let's call it U2. The blue vector is going to be exactly what? The red vector minus the green one. And once I know the blue vector, all I need to do is to compute its length. And its length is the distance I'm looking for. So I know U, happiness, I know this. I need to find out the green vector, U1. Now, what is the green vector? Equal to. What is U2 equal to? And now this is perhaps the only equation that thou shalt have on your sheet, on your cheat sheet. So the rest of the A4, you can do whatever you like with it. Wrap herrings, whatever. Fish and chips. So sorry, I mean U1 here. So what is U1? Now let me give you a subliminal message. I'm projecting my slides on the screen. So U1 is actually what? The okay, so it's the projection of the vector U in the direction of the vector D. And there is a formula for that, which involves, as your colleague is saying, a dot product. So you do U dot product D divided by the length of D square, which is nothing but the dot product of D with itself. And this is going to give you a number that you use to multiply the direction vector. This is the formula for computing the projection of the vector u in the direction of the vector d, which is the direction vector for the line. Okay, during the lecture where we introduced this, we also argued why that's the right formula, but perhaps it's a bit too late now to start thinking about this. Take it as a black box. It works. It's been tested by thousands of years, well, no, perhaps hundreds of years of algebra, of linear algebra. Okay, so now, of course, thou shalt know how to compute the dot product, but that's a piece of cake, isn't it? Okay, so let's see. Let's give ourselves a little bit more of a scratch pad. Okay, so let's rewrite. What is u? U is -1, -1, 1. What is d? D is 1, 0, 1. What is the dot product of those two guys? Okay, how do you compute the dot product? Okay, you multiply the entries in the same position and you sum all the results. Okay, so what is this? Well, it's -1 times 1 plus -1 times 0 plus 1 times 1. Which is 0. Which tells us what? Okay, the two vectors are orthogonal. Okay? So, in fact, we can stop calculating. We already know what u1 is in this case. u1 is, so this is going to be something like 0 divided by something. Times d. Well, what is this? Okay. Well, 0 divided by something is what? 0. So 0 times any vector is what vector? The 0 vector. Okay, so u1 is the 0 vector. So what is u2? It's just u. Okay, so u2, rock away, I will follow, is just u, which is this vector here. Which means that the distance is the length of the vector u. And what is the length of this vector? Absolutely. It's the square root of the square of all of the components. And it's going to be the square root of 3.
Does this mean practically we only have a line in space with a non-orthogonal vector?
Okay, so the question is, does this mean graphically we have a line in space with one orthogonal vector? Well, that's basically what we calculated. I just put values at random here. So this is a recipe that I concocted with values that I concocted on the spot. And what came out was something that led to very easy calculations because two of the vectors were actually orthogonal. Now, the exercise of this type that you solved for test 2, I believe, it involved more calculations than this. If by any chance at the exam you need to solve an exercise like this, make sure that the value of the vectors and of the line, the direction vector for the line, will be chosen so that the numbers remain nice and small. So if you start having to do mind-boggling calculations, you're doing something wrong somewhere. As I've said many times, I'm not interested in figuring out what you can calculate. I assume you can, or I assume you can write a program so that the machine actually does the calculations for you. That's the computer science way. What I'm interested in is that you know the concepts. And for this, I don't need to give you large vectors with humongously large components. At that point, the concepts are drowned into the calculations, which are boring. Okay? So if you see a 6x6 matrix at the exam, you can come and complain. And now I've gone on record as saying you will not see one. And in fact, I know you will not see one because I've already sent the exam paper already yesterday. Don't ask me what's on it, though. Huh? I will not answer. Okay, any doubt about what we've done? The recipe is simple. It's also on my school, in the book. You've used it. It's a foolproof way. I asked Jamie Oliver whether this would work. He said yes. Put it in the oven 170 degrees for 3 hours, and you get a fantastic solution. He knew that the exam was 3 hours, so. But you shouldn't spend 3 hours on this question if you have a question like that at the exam. Okay, another exercise. So let's do a different type of exercise. Suppose somebody tells you, okay, Luca, give me a plane. Well, somebody tells me, sorry, not you. Luca, give me a plane. And I say something like 3x plus 4y plus 2z equals 6. Don't ask me why I picked those numbers. They just came. Okay, so this is the equation for a plane. But now I ask you, let me turn the tables. Somebody asked me for a plane. That was the easy part. Now I ask you to do something for me. I tell you, I have my favorite point. And this point is called 1, 1, 1. Because I like them simple and constant. I want my life to be plain. 1, 1, 1. And now, what I want you to do is to give me the equation for the line that goes through my favorite point and is orthogonal to this plane. So in other words, so here's my plane. Let's say here's my point. I want the equation of the line that goes through this plane and goes like this. Orthogonal. So this is the point, say, the point where this line is going through the plane. So I want the direction vector of the line to go, say, like this. This should be the direction vector of the line. So how would you solve such an exercise? Okay, Baldur here is saying, well, since you want the line to be orthogonal, there is a fairly natural, in fact, the natural way of picking the direction vector for that line is to pick the normal vector for the plane. Okay, so I would actually pick this to be the normal vector for the plane, because the normal vector is, by definition, orthogonal to the plane. So now you put your Sherlock Holmes cap on, you look at what I've told you about the plane, namely that it has this equation, and out of these ingredients, I want you to tell me what the normal vector is. And Elisa is saying it's 3, 4, 2. Why? Because the normal vector, the coefficients for the normal vectors are those that multiply the variables x, y, and z. So n is the vector 3, 4, 2. In fact, Sherlock Holmes is still trying to figure that out, but now he knows. Because Sherlock Holmes didn't follow a linear algebra course, whereas you did, at least in part. I wouldn't call this a linear algebra course. It's sort of just a one-pill version of a linear algebra course, parts of it. Okay? But now, ladies and gentlemen, I have a point, 1, 1, 1. I have a direction vector. And once you have a point and a direction vector, you have what? You have the equation for the line. You have the line. So what is the equation for the line? Well, let's write it in the form which I think is more intuitive, the most intuitive. It just tells us, okay, what is x, what is y, and what is z for all of the points of the line. Well, I want this to go through the vector 1, 1, 1 plus t times the direction vector. So this would be plus 3 times t plus 4 times t plus 2 times t, where t can be an arbitrary real number. Okay, in vector notation, this is what I wrote. That's the point P through which I want my line to go, plus t times the direction vector. And again, t can be an arbitrary real number. Again, how do you solve the exercise? Well, you look at the data that I gave you. I gave you a plane, I gave you a point, and I also told you what I want the line to do. It has to go through the point, and it has to be orthogonal to the plane. Well, now you start your Sherlock Holmes impersonification. Well, since the line has to be orthogonal to the plane, it has to go in the same direction to the normal from the plane, because the normal is orthogonal to the plane. How do I find the normal? Well, I look at the equation for the plane, and the normal just jumps out. It's the vector of multiplying coefficients for the variables. You see, I look at this, and 3, 4, 2 comes out. Especially because Elisa gave it to us, so it just jumped out from her. Okay, and now I have everything, because you know how to write the equation for the line once you have a point and the direction vector. You just plug the data in, no thinking anymore. You already did your thinking before. Now you just feed the formula with the data that your machine learning algorithm figured out. Your machine learning algorithm is your brain, by the way. Any doubt about this? There is silence in the room. I don't know whether there is silence at home right now, but typically I would take this to be a yes, which would mean, given my question, that there are doubts, but I like to think that the answer is no. There are no doubts this time. If there are any doubts, scream now. You didn't get the equation for the line, or this. Down below, this one. Okay, this is another version of writing this. I just say, okay, a vector is on the line, if and only if, so a vector that is on the line should be equal to, should be obtainable by taking the point through which the line goes plus t times the direction vector. So you start from the point and then you follow the direction vector by some amount, by stretching the direction vector sufficiently far, sufficiently long, so that you actually reach the point that you want to reach. In particular, if you take t equals 0, then you stay at the point 1, 1, 1. If you let t grow, then you go away. If you let t become small, 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 small in the negative sense, you take minus 1 billion, then you travel away from t.
So the goal was to find the equation for the line.
The goal was to find the equation for the line. Yes, I thought that. No. The goal was to find the equation for the line. I hope I said that. Okay. Let's do another exercise having to do with lines. So suppose I now give you 2 points, P, which is the origin, 0, 0, 0, so that we calculate as little as possible, and Q, which has coordinates, let's be creative, 1, 2, 3. Okay, what I want you to do now is to give me the equation of the line that goes through P and Q with swirl. So in other words, here's my P, here's my Q, I want that. Well, let's move my Q. I want the equation for this thing. It's a line. Okay, now I gave you 2 points, but no direction vector. Well, what would be a natural way or a good way of choosing our direction vector? Well, it's the vector that goes from P to Q. So I want to go from P to Q. Well, I should go along the way from P to Q. So let's pick as our direction vector the vector that goes from P to Q. And how do I find what it is? Well, it's the difference between 1, 2, 3 and 0, 0, 0, which is nothing but 1, 2, 3. Okay, so give me the line. X, Y, Z is equal to what? 0, 0, 0 plus t times the direction vector, which is 1, 2, 3. Or in other words, it's t times 1, 2, 3, where t is something that you can pick arbitrarily over the real numbers. Again, you've done exercises of this type before. The important thing is the way you approach the exercise, which is always the same. You stare at the data that you have at your disposal. You ask yourself, what is it that I need to answer the question? Well, you want a line, Luca. I need the point and a direction vector. Okay, now, the data gives me 2 points, so I'm cool with that. I have 2, so I can pick one of the 2. What I need is the direction vector. How do I find it? Well, the line should go between P and Q, so why don't I take the direction vector, the one that goes from P to Q? At that point, all you need to do is to plug those data in. The template that you have for the equation for the line, and you're cool. In fact, your neurons haven't even started warming up once you finish solving the exercise. You look at it and you say, wow, give me more, because my neurons are still warming up. They haven't even started doing that. Any questions about this? Okay, so let me give you a variation on this. Well, since we are at it, let's do a further variation. Now, I give you this equation for a line. This equation here that we just figured out. And I tell you, okay, let's consider a point R, and this point is 3, 2, 1. Fantastic, yes. I love that. So now I ask you, can you give me the equation for the line that goes through this point R and is parallel to the line that I gave you, or that you gave me, actually? I'm sure you can. People have already said, yes, we can give it to you. Give it to me. Okay, well, it has to go through this point. So what is the first thing that I write? That point. And now we will have to be something like plus t times, where t is a variable that ranges over the real numbers, some direction vector. Now, which direction vector should I use? The same one as the line to which I'm supposed to be parallel. Because if I'm parallel to a line, I'm actually going in the same direction as that line, only parallel to it. So 1, 2, 3. Because as you might recall, 2 vectors are parallel if one is a multiple of the other. So if I have this line here and this line there, well, they are parallel, or sort of, they look modulo my drawing, and okay, sort of this is the direction vector for this line. Well, in which direction does this line go? It's the same. It's just a translation of that line, but it goes in the same direction. Assuming that I like my lines to go upwards. Okay, so this is the direction vector for both lines. What changes is the point through which the line goes. So, for instance, if you are in Reykjavik and you start traveling northwest, you're parallel to if you're in Húsavík and you start traveling northwest. Your direction is northwest in both cases. You keep traveling, and sooner or later you go towards Jan Mayen or wherever that is. But you proceed parallel. So this would be, well, this is not northwest, this is sort of northeast. So this is Húsavík, and this is perhaps Vik.
Do you always, what I'm asking is, do you always turn the numbers around? Or is it...
Oh, no. So the numbers here are just because one was 1, 2, 3, and the other one was 3, 2, 1. It's so you don't turn the numbers around. Oh, the key thing here is the direction vector. The direction vector is the same, but these are the points through which the line goes. It just so happened that sort of jokingly, somebody actually suggested 3, 2, 1. I picked 3, 2, 1. So you shouldn't read too much. The actual numbers don't matter. What matters is that two lines are parallel if they have the same direction vector. And we are using the direction vector from the other line, absolutely. Okay, I think we are basically done. You didn't ask for it, but I cannot resist giving you some advice. In fact, it's not from me, it's from other people. And this is not just advice for this exam, it's advice for your life, both at the university and in the future. In fact, the future is more important, but if you don't do well, the future will be more difficult than it would be otherwise. First thing, there is no such thing as luck. Well, actually there is, but luck as an act of favoring the prepared mind, as Louis Pasteur, the guy who sort of discovered the principles of vaccination. He's the guy that made us all alive the way we are. So what he said was that luck favors the prepared mind. So you will be perhaps surprised to figure out that some people are luckier than others. Well, it's because these people actually prepare themselves better than others. So at the exam, the luckier people tend to be the people who work that little bit harder to prepare themselves. And it's not just at the exams, it's in real life as well. So how do you get lucky? You think, which is something that you are very well prepared to do. You're thinking machines. Of course, that's not a guarantee of success, because as Leslie Lamport wrote very recently, and he said in a very clear and very truthful way, thinking, the fact that you think about your solution does not guarantee that you will not make mistakes. But not thinking guarantees that you will certainly make a mistake. So always takes this lead. You want to solve some problem, you want to make a good decision, think about it. Then perhaps you still make a mistake, but if you had not thought in the first place, things would be much worse. Now, how do you figure out whether your thinking is clear or not? Write things down. Doesn't mean you have to write novels, but just put your thoughts, your guiding lines behind your solutions on paper. Because as a famous American cartoonist actually wrote, writing is nature's way of letting us know how sloppy our thinking is. So whenever you get an idea a clever solution for whatever problems on your jobs in the future, write them down. Most often than not, it so happens that while you write them down, you realize that they're not so clever and they're not solutions after all. But that's already a start. You've learned something. And I think that this is where I stop, because otherwise then I think this will be another 3-hour lecture, which you're not prepared to listen to. And I'm also going to listen to a seminar right now, so I don't need to speak for at least 45 minutes. Thank you very much for being with me in the course. And I was about to say good luck for the exam, but you don't need it.